Okay, I think I bumped the wrong button on this recording device and shut it off. So I finished this example and I want to talk through it just a little bit here. So let's recall that the instructions said to sketch the functions by identifying zeros, critical points, and inflection points, and then consider the function behavior according to the function's first and second derivatives. So one thing that we did not do in the first example was really consider the zeros associated with the original function. So that's what I've done here in red ink. If you recall, with a fraction, the only way to make this fraction equal to 0 is to set the numerator equal to 0. And when 3x is set equal to 0, then the value 0 will create a 0. So there is a x-intercept, a 0 at x equals 0. Now additionally, this original equation is undefined when the denominator equals 0. That produces either a whole if it's a removable discontinuity or an asymptote if it is a non-removable discontinuity. When factored, we create x plus 1 and x minus 1, which cannot cancel with any factors in the numerator, so we consider these non-removable discontinuities, and therefore vertical asymptotes are created at x equals positive and negative 1. So off to the side, and hopefully you have a little bit of room to do this, or maybe you can sketch this on another sheet of paper if you don't, I might want to just start building the shape of this graph based on the components that we've just identified. When x equals 0, we have a 0 of the graph. The graph does have to touch the x-axis here. When x equals 1, and I'm going to use 2 grid lines for each unit. When x equals 1, we have a vertical asymptote. The graph will not touch. It could potentially cross, but it will not touch or approach, or it does approach this vertical asymptote. Actually, let me clarify that. Horizontal asymptotes can be crossed and touched, but vertical asymptotes generally aren't. But anyway, we've got a graph that's kind of bounded at positive 1 and negative 1. And we've got that from understanding the behavior of our rational expression. Now, the other thing that you might want to consider is the degree of the numerator being 1 and the degree of the denominator being 2. That implies that there's a horizontal asymptote at y equals 0. When this degree is smaller than this degree, when the largest exponent of the numerator is smaller than the largest exponent of the denominator, then we've got a horizontal asymptote at y equals 0. And so the graph itself will tend towards 0 as we extend towards infinity in either direction on the x-axis. So that red marking, or those red markings, are all generated by just our simple understanding of rational functions. Now when it comes to the derivative of this function, well, f prime was calculated by using the quotient rule. And so I took the low function times the derivative of the high function minus the high function times the derivative of the low function. I did the distribution of terms where necessary and multiplication as needed, and then ultimately I was able to combine like terms. What I noticed at the very end was that there was a common factor of negative 3 in both of these two terms, so I wrote it in its factored form as well. I would prefer us to simplify our work from here down, but I'm not going to be picky as to whether we factor out a common factor at the very end or not. I just did so out of curiosity to see if it would be helpful to answer any questions. In this case, I noted that there were no critical points since the function will never equal 0. It's impossible for this numerator to equal 0. X squared plus 1 will never equal 0 with real numbers. Additionally, we know that critical points exist when the derivative is not calculable, when it does not exist. But as it turns out here, the points where the derivative doesn't exist, positive 1 and negative 1, well, those are also the positions where the function is not continuous. And so critical points occur only on continuous portions of a function. And so since the function is not continuous at positive and negative 1, we can't call those critical points. Now, I've drawn two number lines here, and I haven't completed them yet because I noticed I wasn't recording anymore, but in these two number lines, we can perform our first derivative test, our first derivative analysis. And so what I'd like to do is I'd like to investigate what happens to the left of -1, in between -1 and 1, and then to the right of +1. What happens in these three regions in our first derivative? So I'm going to think of a number -2, and I'm going to test it with our first derivative. And this is where this factored form really comes into play. With the number -2, I end up with a negative factor here. -2 squared is a positive number plus 1, so that creates a positive number. And it doesn't matter what I get down here, whether it's positive or negative, because that result gets squared, and I ultimately produce a positive number in the denominator. And so when we have a negative times a positive, produces a negative result divided by another positive. This tells me that in this region, to the left of -1, we have a negative first derivative. The graph must be sloping down. If we perform the same test with a number between -1 and +1, let's say 0, well, again, we get a negative factor. 0 squared plus 1 produces a positive factor. And then, doesn't matter what we get down here, 0 minus 1 is negative, but that negative number gets squared, so we've got a positive result down below, again yielding a negative first derivative. Now lastly, if I perform a first derivative test for the numbers to the right of +1, well, we've got a negative factor here. 1 squared plus 1 produces a positive result, and 1 squared, sorry, not 1 squared, we have to use something other than 1. 2 squared, again, positive result. 2 squared minus 1 is positive, and squared again, so we get another positive result. And interestingly, this region of the graph ends up having a negative derivative as well. And so based on our first derivative test, and even if we don't know anything else about this particular rational function, we're told that the function is decreasing everywhere. The entire function, when read from left to right, will always be decreasing. Now, if you think carefully, that behavior in conjunction with the asymptotes that we established a second ago might give you an idea of what the shape of this graph ought to be. For example, if we're bounded by these asymptotes, we might be thinking there's a branch of the function that exists here. But this particular branch is no good because at any one of these points along this branch, we have a positive first derivative, which can't happen in our current example. We might be thinking in between the two asymptotes of a graph that looks like this. We've seen that before in our rational functions unit. Here we have a graph that touches the x-axis as it should, based on our preliminary work, but we have a negative derivative in this range and a positive derivative in this range, which we know can't happen based on our first derivative test. So that particular shape is no good. Lastly, if we were to try something like this, on the right-hand side, well, we might be onto something because every one of these points contains a negative first derivative. If I were to try to draw the branch captured by the asymptotes over here, well, now we're again dealing with points that contain a positive series of derivatives. So I'm not going to commit to that yet because we still have the second derivative analysis to complete, and the second derivative analysis should definitely confirm our suspicions. Now, the second derivative was a bit challenging to compute. There's no doubt about it. Computing the derivative was a challenge due to the chain rule necessary inside of our quotient rule, but also the algebra that's used to simplify it. So rather than talking you through the entire process, I think what might be good is if I just zoom out a little bit, and hopefully you can still read this. I'll let you pause the video and look through the work that I've done. I did perform the quotient rule as we normally would, low d high minus high d low over low squared. And the only real tricky part was that the derivative of the low function did require the chain rule. So I've got 2 times this group to the first power times the derivative of that inner group. And then I distributed and combined like terms where available and ended up with this solution down at the bottom. There was some interesting factoring that occurred there too. So if you haven't done so already, I'll let you pause the video now and resume playback in a moment, and I'll continue my conversation. Now when we got to this position at the end, it would be helpful to know when the second derivative is equal to 0. And again, we're considering the positions when this when the second derivative equals 0, and that would occur when either 6x equals 0 or when x squared plus 3 equals 0. Well, x squared plus 3 can never equal 0, at least not with a real number solution. And for 6x to equal 0, that happens when x itself is equal to 0. So our second derivative is equal to 0 at 0 as well. That doesn't really change the position of this point, but it does change the behavior of the function, or it likely changes the behavior of the function at that point. We'll be on the lookout for it. The second derivative doesn't exist at positive and negative 1 again, based on these factors, but that's not much of a surprise because the function itself doesn't exist at those points either. So if the function is undefined, then the derivatives would be undefined as well. So I'm going to consider the second derivative test with 4 regions because we had a 0 at, the second derivative equaled 0 when x was 0, and the second derivative didn't exist at negative 1 and positive 1. So those are our delimiters, if you will, here, and now we've got 4 ranges to investigate, 4 intervals to investigate. Now if I use a number like negative 2 to investigate this expression, we would get a negative term here. 6 times negative 2 is negative. Negative 2 squared plus 3 is going to be positive. And we got to be careful down here. Negative 2 squared is positive 4. Minus 1 is a positive number. A positive number cubed remains positive. If we get a negative number as a result here and cube that, well, we could end up with a negative factor down below. But in this case, a negative times positive divided by positive does produce a negative result. So our second derivative is negative in that interval. If we use a number like a negative 1/2, we do end up with a negative expression here, a positive expression here, and a negative 1/2 squared is a positive number. It's a positive 1/4. 1/4 take away 1 is a negative number. A negative number cubed will be negative. So now a negative times positive divided by negative produces a positive second derivative. And we'll continue this process for the remaining 2 intervals, and we'll end up with a negative interval here, negative second degree interval, and then a positive second degree interval. And if you take the time to design your number lines for your first and second derivative tests like I've done here and stack them on top of one another with correlating positions on the x-axis, you can really start to investigate the behavior of the function or the graph of the function without knowing what it actually looks like. In this region here, to the left of negative 1, we've kind of got this point of intersection here, which is kind of helpful. But to the left of negative 1, we've got a function that's decreasing because the first derivative is negative, and it's concave down. So we need to sketch a graph that is decreasing and concave down. In this region here, now the function continues to decrease, or is decreasing function between negative 1 and positive 1. It's decreasing the whole way. But between negative 1 and 0, it's decreasing yet concave up. And then from 0 to 1, it's still decreasing, but concave down. So it changes concavity, and therefore we do have an inflection point here. We weren't certain of it before, but now that we see the change in second derivative, we know that that is an inflection point. Now lastly, on the right-hand side, we have a decreasing function due to the first derivative being negative. While that function is decreasing, it does concave upward. So if you were suspecting what this graph might look like based on the first derivative, hopefully your confirmation, or hopefully you have confirmation now after considering what the second derivative was. So pause the video now, make your final guess as to the shape of this graph, and fill it in this particular template. Resume playback in a moment to check your work. And here's the sketch. And I did confirm this with my TI calculator, so this is the correct image of the sketch. And if you think of all the criteria that we had to work with, it meets all of them. Along this entire branch of the graph, the derivative will be negative, so it's decreasing from left to right all the way across. We had this graph bounded by the asymptote here. We know that it really shouldn't touch or cross this horizontal asymptote, although it technically is possible. We generally don't see that. So it's decreasing the entire way, and it's concave down from negative infinity to negative 1. That's what our first and second derivative tests told us. The function continues to be decreasing as we jumped across this vertical asymptote. And so we may not have really considered this because the function was racing downward, but it's entirely possible for it to jump across this asymptote and start at an infinitely large y value, and then that would give us the ability to continue to decrease. Within that entire interval from negative 1 to positive 1, the function is decreasing, and along this stretch it is concave up, while along this stretch it is concave down. The entire time it is decreasing, yet the concavity does change, and we have ourselves an inflection point right at the center where the concavity did change. For the last branch, we have a function that continues to decrease. Across the entire interval, the derivatives will be negative. Even as this graph extends out to the right infinitely far, there is just the ever so slight negative derivative. It's a downward slope ever so slightly, even as we continue infinitely out to the right. So it's always decreasing according to our first derivative, and yet the second derivative indicates a concavity of a positive or upward concavity, and we do have that here in this sketch. The asymptotes did bound this on the left-hand side and right here in the middle of the graph. So those criteria additionally were met. And as far as our analysis goes, I think we've done a pretty good job of determining the shape of this graph and the behavior of this function. Now I realize that we could have just generated this picture very easily with the graphing calculator, but that's not really what the goal of this problem or the prior problem was. Our ability to interpret the behavior of a function is really important. We can interpret that behavior based on the results of our first and second derivatives. We don't have to have a picture to look at, but we can essentially determine the behavior of that function by performing our analysis as done here. And that is a truly important skill. So with that in mind, here's a challenge question. I have a red graph and a blue graph, and I want to know which of these, the red graph or the blue graph, represents the function, and which one represents the function's derivative. One graph is the derivative function of the other. Can you tell which is which? Pause the video now, try this problem, and resume playback in a moment to check your work. So the answer that I think is true is that the red graph represents the function and the blue graph represents the derivative. And here's my argument, especially when considering the slope of the tangent lines. This red graph, if you look at this position, and presumably this position, each has a slope of 0 when we consider their tangent lines. So if I consider that position on the blue graph, I should see an equation result that equals 0, and that happens in each case. Now, that is true for the blue graph as well. We have slopes of 0 here, and if I look at the red graph, we'll see that the red graph's calculated result is also 0. So looking at only those positions won't guarantee a correct assessment of this particular scenario. So what I did next from here, after I looked at that, is I continued to focus on the red function only. It's a little bit difficult to switch back and forth between the two, so I just continued to focus on the red function. And now, as I started considering different values along this red function, I realized that all of these slopes, the slopes of the tangent lines here, are all negative. And specifically, this position right here is really negative. That's the steepest downward slope that we encounter. And as it turns out, all of these values on the on the blue function are also negative. I'm not talking about slopes at this point, but I'm talking about values. The value of the blue function is in the negative range, and it is most negative right here. So the lowest value of the blue graph correlates to the steepest downward slope of the red graph. Similarly, if we continue to look at data points along the right-hand section of this red graph, the slope of the tangent line becomes greater until we reach a point right here where it's at its greatest, and then it begins to decrease its slope. The slope is continuously positive in this region, but it becomes less and less positive, and that's the behavior that we see in this in this blue graph above. The highest value on the blue graph does correlate to the steepest portion of the red line, and so I'm pretty well satisfied with making my claim. If I was at all concerned about my claim being red and blue, well, let's use that same analysis against the opposite equation, because we did say that at this point the graph is equal to zero. The slope of the tangent line is equal to 0, and that correlates to this red graph and so on. But if I can consider the slopes of my tangent lines here, well, these slopes are all negative. The tangent lines have a negative slope, yet when we look at the computed result for the red graph, those values are all positive. And so that positive value would imply a positive slope on the blue graph, and we just didn't have that, so there's kind of a violation, if you will. So here again, the red function is the red graph is our function, the blue graph is the derivative of that function. Now, to finish out this lesson, I've got another scenario that I'd like for you to consider, and I think we can address parts A through C. We'll skip part D. So I have a series of containers here, and each one is being filled with a constant stream of water. So we're pouring water into these vessels right through the top, and what we're interested in is creating a graph or understanding the behavior of the height of the water line as time passes. So imagine that you went down to fill up your water bottle, and you had each of these 6 water bottles in front of you, and you did so at the bottle fillers around school. That water comes out at a very consistent volume per second, and depending on the shape of your vessel, the height that water level rises might rise at different rates as time passes. Now, in this particular case, this cylindrical vessel, if I start pouring water in, you could probably guess what's going to happen to the height as time passes. At the end of 10 seconds, we're going to reach the highest point of our water bottle, and I want to know what's happening in between. I hope that it doesn't take too much convincing, but the height over time is simply a straight line for that particular vessel. As water gets poured in at a constant rate, that's important. It's constantly flowing in at a regular speed, regular rate. Then the water level's height is going to raise at a constant rate as well. Now, if I were to take a cone in this orientation and hold that under the fountain, think about how the water level would rise here, especially for this initial position. Is the water level height going to raise quickly or slowly at the beginning, and how does that compare to the water level as it's rising towards the end as we reach the highest point? Take a minute and think about the sketch of the height function there. By the end of 10 seconds, we're going to reach the highest point. Think about how that height function will look over time. Well, I would argue that it looks something like this. The height increases very rapidly at the beginning because there isn't that much space at the bottom of that particular cone. But as the water level rises, as we continue to fill, there's more volume that needs to be filled towards the top. This little section needs more water to be filled than this little section down here or down here or down here. Since there's more water needed to fill each of those additional sections, then the rate at which the height is changing is decreasing. Now, the height does always increase, but the rate at which the height increases is decreasing. Hopefully that makes a little bit more sense. Steep at the beginning and less steep as time goes on, but throughout the entire interval, the function itself is increasing. So what about part C? What if I flip that cone over? We had just a large enough hole to pour water in, and it's coming in through the top. In this particular instance, when water reaches the bottom of the vessel and starts filling from the bottom up, what's going to happen to the height function over time? Again, when we are done with 10 seconds, we will have reached the highest point of the water vessel. But what does the graph of height over time look like? Here again, I would make the argument that it would look like this. The height at the beginning is increasing a little bit more slowly than the height towards the end. As the water level reaches this higher position, the height then moves up a bit more rapidly. If we had this vertical scale right in the middle, maybe I should have defined that a little bit more clearly on the first examples. If I had a ruler or something to measure the height right down the middle, how does the height measurement change as time passes? Well, now we start to get into something a bit more interesting. What if we were filling a sphere or this sort of sharp-cornered combined funnel? This almost looks like a muffler or a catalytic converter off of a car. Perhaps it is a catalytic converter, and instead of water passing through, we're considering emissions from our internal combustion engine passing through this. What if that muffler or catalytic converter had smooth edges as opposed to these sharp corners? What would the sketch of the height function look like? So take a couple moments and make your best guess for D, E, and F, keeping in mind that at the end of 10 seconds, that vessel will be filled with water, so we do need to reach the highest point after 10 seconds, but the travel or the behavior in between might differ. Pause the video now and resume playback in a moment to check your work. Now, I'd make the argument that each of the three remaining examples are pretty similar. In the case of the sphere, when water was filling the bottom of that sphere, the height of the water was increasing pretty quickly, but as the sphere got wider and we continued to pour at the same rate, the height of the water in that sphere increased at a slower rate. And I perhaps could have made this a bit more smooth here. I didn't want to make a sharp angle, but it's more of a smooth transition as we change concavity. As we reached higher levels within the sphere, then the water level rose at a faster rate. With that first catalytic converter shape, or muffler shape, whatever you want to call it, CC for catalytic converter, it had a cylinder at the beginning, a cylinder at the end, a cylinder in the middle, and then some sort of cone or conical shape as a point of transition. Now, along the cylinders, I tried drawing perfectly straight lines because the water level would be increasing at a constant rate in each of those portions. So I'm going to kind of mark where those transitions occurred. From here to here, it was increasing at a perfectly straight rate, constant rate. Here it was increasing at a constant rate, and then here again it was increasing at a constant rate. At that point of transition, much like we saw with the two cones above in B and C, we saw that it was increasing a little bit more slowly as the vessel widened up. So we're thinking about as the water level's rising, the water level rises a little bit more slowly through this range because the width of the vessel is increasing. Then we reach that constant rate, and then the width of the vessel starts to decrease. So the rate at which the height changes decreases as well. In a similar sense, Part C behaves a lot like D, but the transitions were even smoother, and the sides were never perfectly cylindrical. So ultimately, the overall shape, I think, is going to be similar to Part D again. I'm sorry, E. But for Part F, I tried to show a little bit more concavity before and after these points of transition. Now, I don't have a device or anything that can show the graphs of these derivatives. We might be able to work on something, though, if we can establish a singular function to determine the volume of these objects. Or for those of you that are comfortable with CAD modeling, if you can model a particular series of objects that all have the same volume, but these 6 different shapes, well, we might be able to perform some analysis on that too using SolidWorks. Anyway, I hope this video helps you out. I know it got a little bit lengthy there, but the content within it is very good. I hope that you find it useful. Thanks for watching.